In the final decades of the 19th century, the world of science stood tall and proud. Physicists believed they had nearly completed their grand quest to understand nature. Newton's mechanics described the motion of planets and apples alike. Maxwell's equations had woven electricity, magnetism, and light into one elegant tapestry. The clockwork universe appeared perfect, predictable, orderly, and complete. The phrase, "physics is finished," echoed through lecture halls and scientific societies. Yet, beneath that confidence, a small, stubborn mystery flickered, one that would soon dismantle the very foundation of classical physics. Amid this era of triumph lived a man who did not seek to overthrow the old order. Max Planck was a quiet, meticulous German physicist. Born in 1858 in Kiel, he was no revolutionary. He believed in the beauty and logic of classical science. He valued order, discipline, and harmony, both in music and in physics. His colleagues saw him as thoughtful, patient, and deeply methodical. Yet destiny has a strange way of choosing its heroes. It was this conservative scholar, not a radical thinker, who would ignite the greatest revolution in the history of physics. In the laboratories of Europe, scientists were wrestling with a peculiar problem. When they heated objects, pieces of metal, blackened boxes, or filaments, the light they emitted refused to follow theory. These blackbodies glowed red, then orange, then white as temperature rose. Classical equations predicted infinite energy at ultraviolet wavelengths, an absurd result. The problem became known as the ultraviolet catastrophe. It was a paradox that mocked the certainty of science. The brightest minds of the age, Lord Rayleigh, James Jeans, and others, tried to fix it, but the equations refused to behave. Energy, it seemed, was misbehaving. Planck approached this mystery with cautious determination. He did not imagine himself as a revolutionary. For him, physics was not about rebellion, but about harmony, finding the mathematical rhythm that matched nature's melody. He sought not to destroy classical physics but to preserve it. And so, in the late 1890s, he began to study the behavior of heat and radiation with mathematical precision. Day after day he calculated, adjusted, and recalculated. His desk overflowed with sheets of numbers, his chalkboard covered with equations that traced the delicate dance between matter and light. For years, Planck tried to fit the experimental data within the old framework. But nothing worked. Every classical formula failed to describe the observed radiation curve. It was as if nature herself refused to obey human logic. Frustrated but not defeated, Planck decided to take a step no one else dared. He introduced a strange assumption, one that made little sense even to him at first. He proposed that energy could not flow continuously, but must be released or absorbed in small, discrete packets. He called these packets quanta. At first glance, this was an act of desperation, a mere mathematical trick to make the data fit. Planck himself admitted it. But sometimes, desperation is the mother of discovery. When he applied his new formula to blackbody radiation, the result matched perfectly with experiment. The impossible paradox vanished. Nature's curve finally made sense. But at a price. This quantization shattered one of the core beliefs of physics, the continuity of energy. To understand how radical this was, imagine a smooth waterfall suddenly transforming into a staircase. For centuries, scientists believed that energy, like water, could flow in any amount, large or small, smooth and unbroken. Planck's idea declared that it could only flow in steps, not streams. Energy was not continuous but grainy. Light was not a wave spreading infinitely, but a collection of tiny, indivisible chunks. This was heresy to classical thinkers. Yet, the mathematics could not be denied. The constant that defined the size of these energy packets, later known as Planck's constant, became one of the most important numbers in science. Its value, though incredibly small, marked the threshold where the familiar laws of physics dissolved and the strange world of quantum mechanics began. Planck had unknowingly cracked open a door that would lead humanity into an entirely new understanding of the universe. In December 1900, Planck presented his results to the German Physical Society in Berlin. The audience listened politely, unaware that they were witnessing the birth of a new era. Planck himself did not realize it either. He saw his work as a temporary adjustment, a bridge to help classical physics cross a rough patch. He did not imagine that his quantum hypothesis would rewrite reality itself, but the seeds of revolution had been planted. The power of Planck's idea lay not only in its simplicity, but in its inevitability. It explained what classical theory could not. It aligned perfectly with experimental data. It offered a mathematical harmony that matched nature's hidden rhythm. And though Planck hesitated to embrace its deeper meaning, others would soon see its potential. Einstein would use it to explain the photoelectric effect, showing that light behaves as both wave and particle. Niels Bohr would apply it to his atomic model, revealing how electrons orbit the nucleus in quantized steps. Werner Heisenberg and Erwin Schrödinger would later transform it into a full theory, quantum mechanics, describing the subatomic world with unprecedented precision. But before all that, there was simply Planck, a lone thinker staring at numbers that refused to fit, daring to make a leap of faith. His quiet courage in breaking with tradition became the spark that ignited modern physics. It was not a thunderous revolution, but a whisper. A simple equation scribbled on a page, holding within it the power to reshape the universe. To appreciate the depth of Planck's contribution, one must understand the scientific world he inherited. 19th century physics was deterministic. Every motion, every event, was thought to follow precise laws. If one knew the position and velocity of every particle, one could predict the future perfectly. There was no room for chance or uncertainty. The universe was a giant clock, wound up and ticking with mechanical precision. Planck's quantum shattered that illusion. Suddenly, energy came in jumps, not flows. Probability replaced certainty. The smooth fabric of reality was revealed to be made of tiny, flickering threads. At first, even Planck resisted the philosophical implications of his discovery. He was uncomfortable with the idea that nature could be discontinuous. He preferred to believe that his quantum was merely a mathematical convenience, not a fundamental truth. But the universe had spoken, and its language was clear. The quantum was real. As his idea spread through the scientific community, it began to attract both fascination and confusion. Some dismissed it as nonsense, others saw it as the key to understanding mysteries that had long defied explanation. Slowly, the quantum began to weave its way into every corner of physics, from the behavior of electrons to the emission of light. The irony of Planck's revolution is that he never sought it. He was a reluctant revolutionary, a man who valued stability but gave birth to chaos, who believed in order but uncovered uncertainty. His story reminds us that progress often begins not with certainty but with doubt, not with answers but with questions. Behind the quiet figure of Planck stood a mind of immense patience and precision. He once said that, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die." His discovery proved those words true. Quantum theory did not conquer classical physics overnight. It took decades of debate, resistance, and refinement. But its truth endured, outlasting skepticism, reshaping science itself. Imagine Planck in his Berlin study, the glow of a gas lamp illuminating his notes, the air thick with the smell of chalk and ink, the ticking of a clock marking each passing moment. Outside, the industrial world roared, factories, telegraphs, electric lights, all products of classical physics. Inside, one man quietly dismantled the very foundation upon which that world stood. His calculations, neat and disciplined, carried within them a spark that would soon ignite the modern age. From that spark emerged the technologies that define our lives today. Every computer chip, every laser beam, every MRI scanner owes its existence to Planck's idea. Without quantum physics, there would be no transistors, no smartphones, no digital universe. The smallest leap in theory produced the greatest leap in human progress. Planck's constant, h, may be tiny, but its impact is infinite. In the grand tapestry of scientific history, few ideas have carried such transformative power. Newton gave us the laws of motion, Einstein gave us relativity, but Planck gave us the key to the invisible, the bridge between energy and matter, between certainty and mystery. His idea revealed that reality is not smooth but quantized, not continuous but discrete. The universe, it turns out, vibrates in notes of quantum energy, each one separated by Planck's constant, composing the silent symphony of existence. The true revolution of Planck's idea lies not only in what it explained but in what it revealed: that our understanding of the universe will always be limited by the scale of our perception. Beneath the visible world lies a deeper order, one that defies intuition and yet governs everything. It is a world where light behaves both as a particle and a wave, where empty space teems with energy, where matter itself dissolves into probabilities. Max Planck's idea was more than a discovery, it was an awakening. It taught humanity that reality is far stranger than we can imagine, that the certainty of the past must yield to the mystery of the quantum. It opened a new frontier of thought, one that continues to expand with every scientific breakthrough. And so, the man who began as a loyal servant of classical physics became the father of modern physics. He did not set out to change the world, yet he changed it more profoundly than he ever dreamed. In his humility, he once said, "I did not think in terms of revolution, but revolutions do not ask permission, they simply unfold, quietly, inevitably, through the minds of those who dare to see beyond the known." In that winter of 1900, as the snow fell gently on Berlin's streets, Max Planck unknowingly shifted the course of human history. His idea, that energy comes in quanta, marked the dawn of a new age. And though a century has passed, the echo of that moment still resonates through every experiment, every discovery, every flicker of light that reaches our eyes. Planck's idea changed not only science but philosophy itself. It forced humanity to reconsider what reality means, to question whether the universe is deterministic or uncertain, continuous or discrete, knowable or forever mysterious. The quantum world became both a mirror and a riddle, reflecting the limits of human understanding. And at the center of it all stands one man, quiet and determined, whose insight transformed the ordinary into the extraordinary. From his equations flowed the principles that govern everything from the heart of atoms to the farthest stars. His work laid the foundation upon which Einstein, Bohr, Schrödinger, and Heisenberg built the grand edifice of modern physics. Max Planck's revolutionary idea was not born from ambition but from necessity, from the stubborn refusal of nature to obey human expectation. It was an act of pure intellect, guided by honesty, patience, and curiosity, and in that act, the universe revealed a secret it had kept for aeons, that the fabric of reality is woven not from continuous threads, but from quanta, tiny pulses of existence, each one carrying the signature of Planck's constant. The revolution he began still unfolds today. From quantum computing to teleportation experiments, from particle accelerators to the study of cosmic radiation, every step we take toward understanding the universe traces back to that single idea. The 19th century gave us machines of iron and steam, the 20th, machines of energy and light. The 21st will be defined by machines of quantum thought, and all of them, in spirit, bear the mark of Max Planck. The world after 1900 did not change overnight. Max Planck's paper sat quietly in scientific journals, waiting for the right minds to see its power. Even Planck himself treated it like a temporary bridge, something useful but not permanent. Yet history has a way of turning small footnotes into foundations. In that modest equation lay the birth cry of quantum physics, a theory that would overturn every assumption humanity held about matter, light, and reality itself. In the years that followed, young physicists began to re-examine the puzzle that had haunted them for decades. How could light behave as both wave and particle? How could energy appear in sudden leaps rather than flowing smoothly? Planck's hypothesis gave them the key, but few were ready to use it. It took another bold mind, Albert Einstein, to take Planck's quantum and hurl it into the center of scientific debate. Einstein, in 1905, used Planck's constant to explain the photoelectric effect. When light strikes a metal surface, it ejects electrons, not continuously, but in discrete bursts. He proposed that light itself is made of individual quanta, particles later called photons. For the first time, Planck's abstract equation became tangible, visible in experiment. What Planck had seen as a mathematical trick became a physical truth. This was the spark that lit the quantum flame. Einstein's boldness gave Planck's idea wings, and soon others joined the flight. Niels Bohr, another rising star, applied the quantum to the structure of the atom. He showed that electrons orbit the nucleus not in any path they please, but in specific, quantized levels of energy. When they jump between these levels, they emit or absorb light, a process perfectly described by Planck's formula. For the first time, the atomic world made sense. The mysterious spectral lines, seen through laboratory spectroscopes, were no longer random. They were signatures of quantum transitions. Nature's language was written in quanta, and Planck's constant was its alphabet. As these ideas spread, physics entered a new era, an age of wonder and confusion. The old certainty of classical mechanics crumbled. Determinism, once sacred, gave way to probability. Reality itself seemed to flicker between states, uncertain until observed. Some physicists resisted, clinging to the comfort of the known. Others embraced the strange, diving headfirst into the mysteries Planck had unveiled. Out of this tension emerged the giants of modern physics: Heisenberg, Schrödinger, Dirac, each one extending Planck's insight into realms he never imagined. Heisenberg's uncertainty principle told the world that one could never know both the position and momentum of a particle with absolute precision. Schrödinger's wave equation described how these quanta evolve in time, not as particles moving along definite paths, but as waves of probability. Dirac merged quantum theory with relativity, predicting particles and antiparticles, matter and antimatter, the building blocks of the cosmos. Every line of their mathematics carried the whisper of Planck's constant, the silent symbol of the quantum leap that began it all. Meanwhile, Planck himself watched these developments with a mix of pride and disbelief. He admired Einstein deeply, but could not fully accept all the implications of quantum theory. The notion that nature might be ruled by chance, that the universe could be fundamentally indeterminate, troubled him. He had sought order, and instead he had uncovered uncertainty. In letters to colleagues, he admitted his discomfort. "I did not think in terms of revolution." Yet the revolution marched on, indifferent to its reluctant founder. As the 20th century unfolded, the consequences of Planck's idea began to shape the real world. The quantum explained why metals glow when heated, why atoms bond, why stars shine. It unlocked the secret of radioactivity, the behavior of semiconductors, and the mechanisms of chemical reactions. From the smallest transistor to the largest galaxy, everything followed rules written in quantum script. Physicists who once studied billiard balls and pendulums now probed the invisible realm of electrons and photons. Reality, once solid and predictable, dissolved into shimmering patterns of probability. Yet the beauty of Planck's revolution lies not only in the microscopic world it revealed, but in the philosophical doors it opened. It taught humankind humility. No longer could we claim to know the universe with absolute certainty. The quantum reminded us that observation changes what is observed, that knowledge itself has limits. It invited poets, philosophers, and dreamers to imagine reality anew, a universe built not of matter and motion alone, but of possibility and mystery. Planck's influence also reached beyond the laboratory. His discovery arrived at a time when the modern world was awakening. Electricity lit the cities, telephones carried voices across continents, machines blurred the line between man and mechanism. And beneath it all, the quantum pulsed like a hidden rhythm, shaping technologies not yet born. Without Planck's constant, there would be no quantum tunneling, no microchips, no lasers, no GPS satellites. Every screen, every digital signal, every fragment of modern communication is a descendant of his equation. He built the mathematical bridge that carries information through the 21st century. But Planck's legacy is not measured only in devices or discoveries. It is written in the courage to question the obvious. When the entire scientific world believed that physics was finished, Planck looked deeper. When equations failed, he refused to give up. His genius was not in rejecting tradition, but in listening to nature's contradictions. He let evidence, not expectation, lead the way. That humility, that willingness to follow truth wherever it pointed, became the essence of scientific progress. As the decades passed, the quantum theory matured. Experiments confirmed its predictions with astonishing accuracy. The more scientists tested it, the stronger it became. Quantum electrodynamics, quantum field theory, quantum computing. Each new branch grew from Planck's seed. Even Einstein's own theory of relativity would one day meet quantum mechanics at the frontier of black holes and the Big Bang. Planck's idea had started a conversation that the universe itself seemed eager to continue. And yet, the deeper we explore, the stranger the world becomes. Quantum entanglement reveals that particles can be linked across vast distances, behaving as one no matter how far apart they are. Quantum tunneling allows particles to pass through barriers as if by magic. Superposition lets them exist in multiple states at once. These phenomena, verified by experiment, challenge our very sense of reality, and all of them trace their lineage back to Planck's single leap of logic. The man who once sought only to fix a mathematical problem had, in effect, rewritten the rules of existence. He turned physics from the study of certainty into the exploration of possibility. He taught us that even the smallest constant can change the course of history. When we speak of the quantum revolution, we speak of a shift not just in equations, but in imagination. Planck's idea forced humanity to see the universe not as a machine, but as a mystery, alive, dynamic, unpredictable. There is a quiet poetry in this transformation. The same mind that loved the harmonies of Bach and Beethoven discovered that nature, too, is built on quantized notes. Each quantum of energy is a musical step in the cosmic symphony. Planck once said that science advances one funeral at a time, meaning that old ideas fade slowly as new ones rise. But his own discovery was different. It did not wait for the old to die. It simply grew too powerful to ignore. Within a generation, it became the foundation upon which all modern physics stood. As wars raged and empires fell, Planck continued his work in Germany. He endured personal tragedy, the loss of his son in World War I, the destruction of his home in World War II, but he never lost faith in the pursuit of truth. He believed that science, though born in struggle, could unite humanity. In his later years, he wrote of the spiritual dimension of discovery, how every law of nature reflects a deeper order, a hidden unity behind the chaos. For Planck, physics was not merely the study of matter, but a window into meaning itself. His idea, now more than a century old, continues to evolve. In laboratories around the world, scientists manipulate individual atoms, control quantum bits, and explore realms where Planck's constant defines the limits of the possible. Quantum computers, powered by superposition and entanglement, promise to solve problems beyond the reach of classical machines. Quantum sensors measure time and gravity with breathtaking precision. The quantum internet, still in its infancy, may one day connect the world in ways unimaginable. All of this, every photon, every atom, every bit, is a living echo of that moment in 1900 when Planck dared to imagine energy as discrete. If one could trace the lineage of modern physics, every path would lead back to him. The Higgs boson, discovered in 2012, the cosmic microwave background radiation, the fusion reactions inside the sun, each is described by quantum laws. Even the mysteries that remain, dark matter, dark energy, the unification of quantum mechanics with gravity, exist within the framework Planck began. His idea was the first thread in the grand tapestry of the quantum universe, a thread that still unravels today. Perhaps the most profound truth of Planck's discovery is that it reminds us of our own limits. Just as energy is quantized, so too is knowledge. We perceive the universe in steps, not in a continuous stream. Each discovery reveals a little more, but never all. there will always be another mystery, another layer beneath the visible. Planck's revolution was not the end of understanding, but the beginning of endless curiosity. And so, the story of Max Planck is not merely about an equation or a constant. It is about the moment humanity learned that certainty is an illusion, and that truth often hides in the smallest details. It is the story of a man who, without intending to, changed the way we see everything, from the flicker of a candle to the birth of a star. His idea redefined science, philosophy, and technology. It reshaped the human journey from the mechanical age to the quantum age. Imagine him once more in his Berlin study as night falls. The lamplight glows softly on his papers. Outside, snow drifts over silent streets. He pauses, gazing at the numbers before him, numbers that do not quite fit, until he dares to see them differently. In that instant, between calculation and intuition, between reason and revelation, the universe shifts. One man, one idea, one constant. From that quiet moment comes a new reality, a new science, a new future. Max Planck's revolutionary idea did more than change physics. It changed the story of human thought. It showed that even the smallest act of imagination can open infinite worlds. The quantum is not just a theory. It is a reminder that reality itself is born from possibility, that every discovery begins with a question, and that sometimes the universe answers in whispers rather than shouts. Over a century later, every physicist who measures a quantum of light, every engineer who designs a microchip, every thinker who wonders about the nature of existence, stands on the shoulders of Max Planck. His constant, 8, links the measurable to the mysterious, the finite to the infinite. In that single symbol lives the bridge between the known and the unknown. And so the story comes full circle. The man who began with a problem about glowing metal gave humanity a vision of the cosmos itself. He sought a simple equation and found a new reality. His revolutionary idea became the heartbeat of modern physics, the pulse beneath all progress. From one quiet German physicist came a revelation that reshaped time, matter, energy, and thought. Max Planck's name will forever stand at the dawn of the quantum age. The moment when the universe revealed, through him, that even its smallest parts can hold infinite wonder. At the twilight of the 19th century, science stood at a magnificent peak. Physicists gazed upon a world they believed they finally understood. Newton's mechanics described the dance of planets and pendulums with flawless precision. Maxwell's equations united electricity, magnetism, and light into one grand harmony. Thermodynamics explained the flow of heat and energy. To the scientific mind of the era, the universe was a clockwork machine, precise, predictable, and complete. Many declared with confidence that there was little left to discover. But hidden in the glow of an ordinary heated object, nature was keeping a secret, one that would soon unravel the very laws that gave science its pride. In laboratories across Europe, physicists were experimenting with a peculiar phenomenon known as blackbody radiation. A blackbody is a perfect absorber, an object that swallows all radiation falling upon it and emits energy purely based on its temperature. The color and intensity of its glow reveal the rhythm of its thermal dance. When cold, it radiates faintly in red. When heated further, it blazes orange, then white, and finally blue as its temperature soars. It was the most fundamental behavior of matter under heat, simple, pure, and universal. Yet when scientists tried to describe this radiance using the laws they trusted most, something horrifying emerged. The mathematics broke. The universe refused to obey. The story begins with a question that seemed almost trivial. How does the energy emitted by a blackbody depend on its temperature and the wavelength of light? Experiments were clear. At low frequencies, the emitted energy rose smoothly, peaked at a certain point, and then fell at higher frequencies. But when theorists used classical physics to predict this curve, disaster struck. According to their equations, as the frequency increased, the energy emitted should skyrocket toward infinity. In other words, a hot object should produce infinite energy at ultraviolet wavelengths. The equation suggested that the world should glow with boundless intensity. Yet, Clearly, it did not. This absurd prediction became known as the ultraviolet catastrophe, a crisis so deep that it threatened to shatter the very foundation of physics. No matter how brilliant the scientist, no one could explain it. Lord Rayleigh and James Jeans proposed formulas that worked at low frequencies but failed disastrously at high ones. Wilhelm Wien offered another law that worked in the opposite regime, high frequencies but not low. The experimental curve lay between them, mocking every attempt at explanation. Something was fundamentally wrong with the old understanding of energy and radiation. In Berlin, Max Planck watched this crisis unfold with growing fascination. He was a man of patience, of discipline, and of faith in reason. He did not seek to overturn the great theories, he admired them. Yet, as a true scientist, he could not ignore when nature whispered of something new. For years, he had studied thermodynamics and radiation, searching for mathematical harmony between theory and experiment. The Blackbody problem became his obsession. Every failure by others only deepened his determination to solve it. He began by carefully studying experimental data collected by Heinrich Rubens and Ferdinand Kurlbaum. Night after night, he compared their results with every theoretical model he could find. He plotted curves, adjusted parameters, refined constants. Nothing fit perfectly. The data refused to yield to the comforting logic of classical physics. It was as if light itself was playing by different rules. Planck felt both frustration and awe, for in this stubborn mystery, he sensed something profound. To appreciate his challenge, one must imagine the mindset of the time. Energy in classical thought was continuous. Like water flowing from a tap, it could vary smoothly in any amount. The idea that energy could come in chunks was unthinkable, absurd, even. But mathematics is a merciless teacher. Planck realized that no continuous model could produce the observed curve. The experimental data dropped off sharply at high frequencies, and nothing in classical theory could cause that cutoff. Something, somewhere, had to break the flow. In a moment of bold desperation, Planck took an extraordinary step. He decided to treat energy as if it were emitted in discrete packets, not as a continuous stream. He assumed that oscillators, the microscopic particles vibrating within matter, could only radiate energy in multiples of a basic unit, proportional to their frequency. He wrote it as E-tuck, where E is energy, lo is frequency, and h is a tiny constant of proportionality, now known as Planck's constant. He did not yet know what this meant physically. To him, it was a mathematical device, a trick to make the formula work. But when he applied it to the Blackbody spectrum, the result was breathtaking. The curve matched the data perfectly. Every experimental point aligned with his equation. The catastrophe vanished. Nature, once again, made sense, but only under this strange new assumption. Planck had done it. He had solved the Blackbody problem. But in doing so, he had cracked open a door to an entirely new universe. For if energy is not continuous but comes in packets, then the very foundation of physics must be rewritten. Light, matter, heat, all must obey this hidden quantization. At first, Planck resisted the full meaning of his discovery. He described his solution with caution, almost reluctance. He called his constant a formal assumption, not a physical law. But the truth could not be denied. The numbers fit too perfectly to be coincidence. The scientific community greeted Planck's work with curiosity, not revolution. To most, it was just another clever fix, but a few sharp minds recognized something deeper. In 1905, Einstein used Planck's constant to explain the photoelectric effect, showing that light behaves as if it consists of particles, not waves. His paper was like lightning striking the horizon, illuminating the vast landscape of quantum reality. Planck's mathematical trick had become a law of nature. The Blackbody problem had not merely been solved. It had transformed science forever. To understand how profound this was, imagine what it meant for centuries of belief. Classical physics saw the universe as smooth and continuous. Planck's idea introduced a jagged rhythm beneath the surface, a digital beat within the analog symphony of nature. Light, once thought to be a flowing wave, now revealed itself as a shower of indivisible quanta. The blackbody was not just an experimental curiosity anymore, it was the key to the quantum world. In retrospect, the blackbody radiation problem was the perfect gateway to this discovery. It sat at the intersection of thermodynamics, electromagnetism, and atomic theory, the crossroads of classical physics. Solving it required breaking free from the assumptions that bound all three. Planck's equation bridged the gap between the macroscopic and the microscopic, between heat and light, between the known and the unknown. Yet, the beauty of the story lies in its irony. Planck, the reluctant revolutionary, had no intention of founding a new science. He was simply trying to reconcile theory with data, to restore order to physics. But nature rewards those who listen closely. In his search for harmony, he uncovered the discord that revealed the next great symphony of science. The blackbody problem also marked a turning point in how scientists understood reality. Before Planck, physics was deterministic. Every cause had a predictable effect. After Planck, uncertainty crept in, not as ignorance, but as an intrinsic property of nature. The universe no longer followed a smooth script, it played a game of probabilities, where each outcome depended on chance and observation. This shift in thought would later give rise to the profound paradoxes of quantum mechanics, where particles exist in multiple states, and observation shapes reality itself. Still, in 1900, none of that was visible. What stood clear was that the problem, once thought impossible, was now beautifully solved. The ultraviolet catastrophe was gone. Planck's constant became one of the pillars of modern science. The blackbody radiation curve, once a source of chaos, became the first map of the quantum landscape. Imagine, for a moment, the scene in Berlin on December 14, 1900. Planck stands before the German Physical Society, presenting his findings to a room of attentive scholars. His words are precise, his tone humble. He describes his new formula, his assumption of quantized energy. The audience listens, unaware that history is being made in that quiet hall. There is no applause, no celebration, just polite nods. And yet, from that unassuming moment, the world would never be the same. Outside the lecture hall, the air is cold, the city alive with the hum of early modernity. Electric lights, horse-drawn trams, the sound of progress. But within that room, something deeper glows, the birth of quantum physics. The blackbody problem, once a riddle that mocked human intellect, had yielded its secret. And that secret would soon change everything. As the years passed, the full implications of Planck's discovery began to unfold. Quantum mechanics grew from his seed, reshaping our understanding of atoms, molecules, and the fabric of space-time itself. The technologies that now define civilization, computers, lasers, nuclear energy, GPS, and more, all trace their origins to that one insight born from the blackbody. The problem that once symbolized failure became the cornerstone of modern science. The mystery of blackbody radiation had been more than a technical puzzle. It was nature's way of testing human curiosity, of asking whether we could see beyond the visible, whether we could abandon the comfort of certainty and step into the unknown. Planck's success proved that true discovery often begins not in triumph, but in confusion, in the courage to accept that the universe is more complex, more beautiful, and more mysterious than our theories allow. When historians look back on the evolution of physics, they often mark the year 1900 as the beginning of modern science. It was the year when the smooth veneer of classical certainty cracked, and through that crack, the light of the quantum world began to shine. The blackbody radiation problem was the first signal that the old order was ending, and that something extraordinary was beginning. Max Planck would later receive the Nobel Prize in Physics in 1918 for this work. Yet, even then, he remained modest, almost detached from the revolutionary storm he had set in motion. For him, it was not about fame or glory. It was about truth, the quiet satisfaction of bringing harmony to chaos. And perhaps that is the deepest lesson of the blackbody mystery. That nature reveals her secrets not to those who shout the loudest, but to those who listen the most carefully. The glow of a blackbody is a simple thing, the warmth of a stove, the light of a filament, the radiance of a star. But hidden within that glow is the entire history of the quantum universe. Every photon that leaves its surface carries the mark of Planck's constant, the rhythm of quantized energy. When we look at the night sky, we are seeing not just starlight, but the echo of that discovery, the fingerprint of a truth that began in a Berlin lab more than a century ago. The mysterious problem of blackbody radiation was more than an experiment gone wrong. It was the doorway to a new understanding of existence. And the man who opened it, Max Planck, did so not with rebellion but with reason, not by rejecting the old, but by listening to it until it revealed something new. The year was 1900, and deep inside Max Planck's Berlin study, a small coal stove glowed softly against the winter chill. Its orange light danced on the walls, throwing shadows that flickered like thoughts in his restless mind. Outside, snow muffled the city's noise, but inside, equations murmured in silence. For weeks Planck had stared at those symbols, the strange relation between energy, frequency, and temperature. Now that his equation finally fit the data, he should have felt triumph. Yet something in him whispered that the victory was far greater, and far more dangerous, than he imagined. He had just proposed that energy is not continuous, but comes in packets, quanta. It sounded innocent, even trivial. But to a physicist raised on the smooth determinism of Newton, it was as though he had cut reality into pieces. If energy was quantized, then every vibration in the universe, from a glowing atom to the pulse of a star, obeyed a hidden rhythm, a microscopic staccato beneath the flowing music of existence. Planck did not yet know it, but he had just placed the first note of an entirely new symphony. In the days following his lecture to the German Physical Society, Planck's colleagues congratulated him politely. Few understood what he had done. To them, his formula was a clever fit to stubborn data. But Planck himself could not sleep. He spent night after night trying to justify the equation from first principles. Why should energy behave this way? What mechanism could force oscillators to emit energy in chunks instead of a smooth stream? The more he thought, the more he realized that he had stepped onto unfamiliar ground, ground that stretched far beyond classical reasoning. Around him, Europe stood on the edge of a new century. Trains thundering across the continent, telegraphs sending messages faster than thought, and electric bulbs turning night into day. The world was glowing brighter, and Planck's equation explained the very nature of that glow. Every incandescent filament, every ember, every star in the sky was a blackbody, obeying his law. His discovery connected human invention with cosmic design, yet behind the beauty lay a subtle terror. If energy came in quanta, then the smooth tapestry of classical physics was fraying. Planck's constant, that tiny number eshed 6.26 Js, became the smallest unit of action in the universe. It told physicists that nature had a graininess, a minimal tick in the rhythm of reality. It was as if the cosmos, once thought continuous, now pulsed like a heartbeat. Every vibration, every exchange of light or heat, occurred in multiples of this microscopic unit. Nothing smaller could exist. For months, Planck wrestled with the meaning of his own constant. He tried to link it with entropy, thermodynamics, and electromagnetism. Slowly, he began to see that the quantization of energy was not merely a mathematical convenience. It was a fundamental truth. But still, he hesitated to say it aloud. The physics community was not ready for such heresy. Then, in 1905, a young patent clerk in Bern read Planck's papers and saw what even Planck had not dared to imagine. Albert Einstein realized that if energy came in quanta, then light itself must consist of discrete packets, photons. Where Planck had spoken of hypothetical oscillators in matter, Einstein extended the idea to light waves themselves. The photoelectric effect, long unexplained, suddenly made sense. Light could knock electrons out of metal only if its quanta carried enough energy, E.h. With one stroke, Einstein gave physical reality to Planck's constant. The mathematical trick became the heartbeat of the universe. This was the true resolution of the blackbody mystery. not merely a fit between theory and data, but a revolution in the concept of light and energy. The ultraviolet catastrophe had been born of an assumption that energy was continuous. Planck's quantization cured it by limiting how much energy could be emitted at high frequencies. The infinite storm of ultraviolet energy vanished because nature allowed only discrete emissions. It was like replacing a raging waterfall with a stream of pearls, each falling separately, each carrying a precise measure of energy. As the 20th century unfolded, the implications of this new idea rippled outward. Quantum theory began to emerge from Planck's seed. Bohr used it to model the atom, showing that electrons could occupy only discrete orbits. De Broglie, Schrödinger, and Heisenberg transformed it into wave equations and uncertainty principles. But beneath all these revolutions lay the same quiet constant: Planck's H. Every calculation, every experiment, every paradox traced its lineage back to the blackbody glow that once puzzled scientists. The blackbody radiation problem had done more than expose a flaw in classical theory. It had revealed a hidden layer of the universe. It showed that even the simplest phenomenon, the color of heat, could conceal mysteries that rewrite reality. When a piece of iron turns red, orange, and white as it heats, we are witnessing quanta in motion. Each photon released is a note in nature's quantum melody. Imagine, for a moment, the sun. Its surface at 6,000 Kelvin radiates like a vast blackbody. The sunlight that warms Earth follows Planck's distribution almost perfectly. Every sunrise is a living demonstration of his law. The color of the morning sky, the warmth on human skin, the balance of light and life, all are governed by that constant born in a Berlin laboratory. From the glow of a candle to the birth of galaxies, Planck's discovery unites the microcosm and the macrocosm. Yet, behind this triumph lies a deeply human story. The story of a man who believed in order, faced chaos, and chose reason over pride. Planck was not a rebel like many later quantum pioneers. He was conservative, methodical, even skeptical of change. But when confronted with nature's contradiction, he bowed to evidence. His courage was not in defiance but in acceptance, the quiet bravery of admitting that the universe was stranger than his beliefs. In the years that followed, Planck watched younger physicists push his idea far beyond what he had intended. Heisenberg's uncertainty principle, Schrödinger's wave mechanics, and Dirac's quantum fields painted a world of probabilities rather than certainties. Planck admired their brilliance but often felt uneasy. The new quantum theory abandoned determinism, a notion he still cherished. Yet, deep down, he knew that his own equation had started this transformation. He had lit the first spark that now burned across the landscape of science. By the time he received the Nobel Prize in 1918, the world had changed. Einstein's relativity was reshaping space and time, and quantum physics was redefining matter and energy. The blackbody problem, once a technical curiosity, had become the cornerstone of modern physics. Scientists could now calculate the radiation of stars, the temperature of the cosmos, and even the energy levels inside atoms, all using Planck's law. But the story did not end there. Decades later, when physicists measured the faint glow left from the birth of the universe, the cosmic microwave background, they found that it followed the blackbody spectrum with astonishing precision. The universe itself, born in fire, carries the signature of Planck's discovery. The same equation that described a glowing piece of metal now described the entire cosmos. The blackbody problem, once confined to a lab, had become the voice of creation. It is poetic to think that the greatest mystery of the 19th century gave birth to the greatest theory of the 20th. The ultraviolet catastrophe was not a failure but a doorway, a point where the old logic collapsed, forcing humanity to see the world anew. Every age faces such a moment when certainty dissolves and imagination must take its place. For Planck, that moment came in the gentle glow of thermal light. For us, it reminds that progress often begins in paradox. Even today, Planck's constant remains one of the defining numbers of the universe. It tells us how the smallest things behave, how electrons jump, how atoms emit light, how time and energy intertwine. It sets the scale of the quantum world, the line between the continuous and the discrete. In 2019, scientists even redefined the kilogram based on Planck's constant, immortalizing his discovery not just in theory, but in the very standards of measurement. The constant born to solve a riddle of heat now anchors the foundation of reality itself. And yet, beyond its equations, the Blackbody story holds a deeper lesson about humility. Physics in Planck's time had grown arrogant, confident that it could explain everything. But nature humbled it with a single question. The Blackbody problem reminded humanity that every answer is temporary, every law provisional. The universe always has another layer, waiting for those who dare to look closer. Picture the laboratories of that era: gas lamps hissing, prisms splitting light into spectra, glass bulbs glowing under electric current. Scientists measuring brightness with photometers, writing data by hand, unaware that each number recorded was whispering about the quantum world. They sought to measure heat. Instead, they measured the limits of knowledge. In their instruments, light carried a secret, a pattern that only Planck's equation could unveil. The triumph of the Blackbody solution was not just mathematical precision, but conceptual liberation. It taught physicists that the laws of the small need not mirror the laws of the large. The atomic world had its own logic, a strange, statistical, unpredictable dance. From that realization would come lasers, transistors, quantum computers, and the entire digital age. The modern world, with all its light and technology, is the grandchild of Planck's furnace. As Planck grew older, he often reflected on the irony of his life. He had entered physics hoping to bring order, not upheaval. He had dreamed of refining the great laws of thermodynamics, not destroying them. Yet history remembers him as the father of the quantum revolution, a title he accepted with both pride and melancholy. He once said, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die, and a new generation grows up that is familiar with it." It was a statement born of experience. The revolution he had ignited took decades to be fully believed. The Blackbody radiation problem stands as one of the most beautiful moments in the story of science. Not because of the catastrophe it caused, but because of the clarity it brought. It showed that even in the heart of failure lies the seed of discovery. Planck's willingness to question the unquestionable transformed physics from a clockwork universe into a living, breathing reality of quanta and possibilities. Today, when scientists study the light from distant stars, when they cool atoms to near absolute zero, when they manipulate photons to create quantum networks, they are, in essence, continuing Planck's work. Each experiment echoes that moment when he dared to imagine that energy could be discrete. The Blackbody, once a simple furnace for studying heat, became a cosmic symbol of quantization, the bridge between the human and the infinite. And so, in the quiet glow of every lamp, every sunrise, every star, there lives the memory of that discovery. The colors of the universe are not continuous shades, but a symphony of quantized notes, each following Planck's law. The warmth we feel, the light we see, the very act of observation, all trace back to the mystery of a Blackbody's glow. Max Planck's journey began with confusion and ended with creation. He entered the unknown, armed only with reason and curiosity, and emerged with the constant that governs all existence. The mysterious problem of Blackbody radiation was his trial by fire, and through it, he gave humanity the key to the quantum world. Even now, more than a century later, when we look into the night sky, every star radiates according to his equation. Each photon traveling across the void carries with it the same story. The story of a universe quantized, structured, and alive with energy. And in that endless light, we still hear the echo of Planck's realization that the smallest idea can illuminate the greatest mystery. In the dawn of the 20th century, when humanity believed it had nearly solved every riddle of nature, a quiet revolution was forming in the invisible world. Physics had reached what many thought was perfection. A majestic cathedral built from Newton's laws, standing firm on the pillars of determinism and reason. But in its deepest chambers, a crack began to appear. The old world of continuous motion, smooth waves, and infinite divisibility could no longer explain the flicker of heat, the dance of atoms, or the spectrum of light. Something small, something indivisible, something unseen was waiting to be discovered. And it came not with thunder, but with a whisper. The birth of the quantum. When Max Planck proposed that energy could only exist in discrete packets, he did not merely solve a problem. He created a new reality. His quanta were not just a mathematical tool, they were the universe's secret syllables, the smallest fragments of action through which nature speaks. It was as if reality itself was pixelated, its smoothness an illusion born from vast numbers of microscopic jumps. Each packet of energy, each quantum, carried a definite measure, eta hum, where h was Planck's constant and null the frequency of radiation. No smaller step existed. The cosmos, once imagined as a flowing river, was in truth made of countless droplets. This was more than a theory, it was a profound philosophical shift. For centuries, the idea of continuity had ruled science. From Aristotle's belief that matter was infinitely divisible, to Newton's seamless space and time, to Maxwell's elegant waves of light, everything in nature seemed to follow an unbroken chain. The notion that energy could jump, that nature might stutter between one state and another, felt almost blasphemous. Yet Planck's equation demanded it. Energy did not flow like water, it came in bursts, in indivisible packets, each carrying a fixed quantum determined by its frequency. At first, few understood what this truly meant. To most physicists, it seemed like a mathematical trick to make the equations fit experimental data. Even Planck himself viewed his discovery as a temporary fix, not a universal truth. But deep beneath the skepticism, a new order was emerging. The quantum had entered physics, and it would never leave. To grasp the magnitude of this transformation, one must imagine how the world looked before the quantum. Light was thought to be a wave, a continuous oscillation that carried energy smoothly through space. Matter was made of atoms, but their behavior was described by classical mechanics. Heat, radiation, magnetism, all were understood as continuous exchanges of energy. But the experiment said otherwise. When light struck metal, it did not release electrons gradually, it did so abruptly, as though exchanging a single coin of energy. When gases emitted light, they produced sharp lines in spectra, not continuous rainbows. Nature was sending messages in code, and Planck had found the first symbol of that code, the quantum. This single insight, that energy is quantized, transformed every corner of physics. It laid the groundwork for Einstein's photon, Bohr's atomic model, and the entire structure of quantum mechanics. But in its infancy the idea was fragile, too radical for most, too subtle for the age of classical certainty. Even Planck hesitated to accept its full meaning, yet history often rewards those who listen to whispers before the world is ready to hear them. In the years that followed his 1900 discovery, Planck's constant began to appear everywhere, like a signature woven into the fabric of the cosmos. In the photoelectric effect, it measured how light ejects electrons. In Bohr's atom, it defined the spacing of electron orbits. In Heisenberg's uncertainty principle, it became the very limit of what can be known. Planck's tiny number, 6.626 × 10^, became the heartbeat of the quantum world. It told humanity that there was a smallest action, a smallest transfer, a smallest step, below which nature does not go. It is difficult today to appreciate how shocking that was. Imagine centuries of faith in smoothness, from planetary motion to musical harmony, suddenly replaced by a world made of jumps, leaps, and discontinuities. The laws of nature were no longer a continuous melody, they were composed of notes, finite and precise. Light itself, that most ethereal of entities, was now a stream of particles. Energy had become countable. The infinite had become discrete. This new vision of reality did not come easily. Even after Planck's discovery, most physicists clung to the classical picture. The quantum seemed absurd, an insult to the elegance of the universe. Einstein, though he extended Planck's idea to light, struggled for decades with its consequences. Bohr embraced it but found himself building a theory that defied intuition. Schrödinger, trying to restore continuity, invented wave mechanics, only to find that probability had replaced certainty. Heisenberg reduced the universe to matrices of numbers that could predict results but not explain them. Every step forward in quantum theory seemed to dissolve another piece of common sense. And yet, through all this chaos, Planck's original insight remained solid: energy comes in quanta. It was the seed from which the forest of modern physics grew. Without it, there would be no atomic theory, no lasers, no semiconductors, no computers. The quantum became the foundation upon which the future was built. But behind this monumental shift was also a profound human truth: that discovery often begins with discomfort. Planck was not seeking to overturn physics, he was trying to preserve it. His quantization was an act of desperation, a last resort to reconcile theory with experiment. Yet it was precisely this humility before evidence that made his work immortal. He had looked at nature not as a conqueror, but as a listener. And in her faint, paradoxical whispers, he heard something no one else could: that energy is not a smooth flow, but a rhythmic dance of quanta. In every corner of modern science, the quantum now reigns. When an atom emits light, it does so in discrete jumps between energy levels, each jump releasing a photon whose energy equals the difference between those levels. When electrons flow through a semiconductor, they tunnel and leap according to quantum rules. Even the empty space between particles seethes with virtual quanta, appearing and disappearing faster than we can imagine. The quantum world is not an exception, it is the foundation. What we perceive as continuous reality is merely the blurred sum of countless quantum events, too small for our senses to resolve. To understand this intuitively, imagine standing beside a fast, flowing river. From a distance, it looks smooth, but up close, you can see that it is made of countless droplets, each with its own path, its own motion. The river's smoothness is an illusion of scale, so too is the world's apparent continuity. The universe we inhabit is not a smooth film but a frame-by-frame reality, with Planck's constant setting the frame rate. At this scale, time and space themselves begin to tremble. The quantum world does not obey our logic of cause and effect, it dances to probabilities. Particles can be waves, waves can be particles, and energy can flicker in and out of existence. Yet all of it, every paradox, every mystery, begins with Planck's first step, the quantization of energy. That was the spark that lit the fuse of modern physics, the small idea that shattered the great edifice of classical certainty. Planck's own reaction to this revolution was deeply human. In his later years, he confessed that he had never truly believed in quanta as physical entities, not in the way Einstein or Bohr did. To him, they were mathematical constructs, not real particles of energy. Yet, ironically, his cautious invention became the most radical concept in the history of science. It was as if he had opened a door without realizing that behind it lay an entirely new universe. And what a universe it was! The birth of the quantum changed not only how physicists saw the world, but how humanity thought about reality itself. It replaced certainty with probability, continuity with discreteness, determinism with chance. It suggested that the universe, at its core, is not a clock but a song, played on the smallest scales, each note quantized, each beat defined by Planck's constant. If one could listen to the universe at that scale, one would hear the rhythm of energy packets being exchanged, the hum of photons born and absorbed, the crackle of atoms leaping between states. Every flash of light, every shimmer of heat, every breath of radiation is the echo of that quantum rhythm. The world is not still, it flickers with energy, like the pulse of an invisible heartbeat beneath all matter. The story of the quantum's birth is, in truth, a story about perception, about learning to see what was always there but hidden from view. The ancients looked at the stars and saw permanence, Newton looked and saw force, Maxwell saw waves, Planck saw quanta. Each step was a deepening of vision, a refinement of what humanity could perceive. The quantum was not an invention, it was a revelation. It was as if nature had always been quantized, but only now had someone adjusted the lens enough to notice, to realize that even light, that most continuous and gentle thing, was made of discrete particles required a leap of imagination as great as any in human history. Planck had crossed a threshold that no scientist could uncross. From that moment onward, the universe was forever divided into two realms, the classical and the quantum, one smooth and familiar, the other granular and strange. The line between them was drawn by h, Planck's tiny constant, small enough to go unnoticed by the everyday world, yet powerful enough to govern everything within it. It is tempting to think of the quantum as merely a scientific principle, but in truth, it reshaped the human view of existence. It told us that certainty is an illusion, that nature operates through probabilities, and that the smallest things can dictate the largest outcomes. From the orbit of electrons to the life of stars, everything obeys this rhythm. Planck's idea, born in a quiet moment of despair, became the foundation of the modern age. In the aftermath of Planck's bold step, the scientific world was left standing on the edge of something vast, something unsettling. His idea of quantized energy, energy emitted or absorbed in fixed packets, had cracked open a door that few yet dared to peer through. To most physicists of his time, it seemed absurd. Energy, they believed, flowed like a smooth river, not like drops from a leaking faucet. Yet Planck's tiny quanta, invisible and indivisible, carried within them the power to reshape our understanding of the universe. As the new century began, that quiet notion began to ripple outward. One by one, scientists confronted the strange implications of this idea. In laboratories across Europe, instruments flickered, experiments failed, and numbers refused to align with old theories. The certainty that had defined classical physics for centuries began to waver. The universe was revealing a deeper rhythm, one built not on continuity but on discrete bursts of action. It was as if nature itself whispered in steps, not in smooth transitions. For Max Planck, the journey was both thrilling and troubling. He was a man of deep rationality, cautious by nature. He hadn't set out to overturn physics, he wanted only to solve a problem. Yet as he studied the equations, as he realized that his constant h defined a new limit to how energy behaved, he began to sense the gravity of his discovery. It was as though he had stumbled upon a forbidden truth, a truth that light, heat, and matter all pulsed in quantized beats. He later confessed that he had been led to this assumption against his will, for he saw how deeply it contradicted the accepted principles of his era. Meanwhile, others began to explore this new landscape. In 1905, a young patent clerk named Albert Einstein took Planck's idea further, applying it to light itself. Einstein proposed that light wasn't just a wave, it behaved as if it were made of discrete quanta, later called photons. With that single insight, he explained the photoelectric effect, how light could knock electrons out of metal surfaces. The result was revolutionary. Light, once thought to be purely continuous, carried particles of energy. Planck's abstract constant suddenly gained physical meaning, and the quantum world began to take form. This was no longer a small correction to physics, it was a reimagining of reality. If light was quantized, then perhaps everything was. The very fabric of the universe was woven from discrete threads of energy, each governed by Planck's mysterious constant. The old notion of determinism, the belief that everything could be predicted if one knew the initial conditions, was being dismantled piece by piece. The certainty of Newton's universe was replaced with the shimmering uncertainty of the quantum world. As this new understanding spread, it changed how scientists viewed the atom. The atom was no longer a miniature solar system with electrons orbiting predictably around a nucleus. Instead, it became a vibrating cloud of possibilities, where energy levels could shift only in precise steps, Planck's quanta. When an electron jumped from one level to another, it emitted or absorbed a quantum of light, a photon, with energy equal to Planck's constant multiplied by its frequency. This was the heartbeat of matter itself, a rhythm that echoed from the tiniest particles to the stars. In laboratories, this principle found astonishing confirmation. Spectral lines, once mysterious streaks of color seen through a prism, were suddenly understood as fingerprints of quantum jumps within atoms. Each element sang its own quantum melody, defined by the discrete transitions of its electrons. What had seemed random and inexplicable became a beautifully ordered symphony of quantized energy. Planck's idea had turned chaos into harmony. The scientific community began to recognize the depth of Planck's revolution. Heisenberg, Schrödinger, and Bohr soon built entire theories upon the foundation he had laid. Quantum mechanics emerged, a framework so successful that it could predict phenomena with astonishing precision, yet so strange that even its founders often struggled to believe it. Planck's constant appeared everywhere: in the uncertainty principle, in atomic spectra, in the behavior of electrons and photons alike. It was the signature of the quantum world, a cosmic scale marking the boundary between the possible and the impossible. And yet, despite its success, the quantum idea also brought philosophical unease. It suggested that reality itself was not smooth and continuous but grainy, uncertain, probabilistic. Nature, it seemed, did not unfold in an unbroken flow. It flickered, danced, and chose among possibilities. This notion shook the foundations of human understanding. Even Einstein, one of its architects, struggled with it, famously declaring, "God does not play dice with the universe." But Planck, ever the patient observer, accepted that the universe might not conform to human intuition. To him, the quantum was not chaos, it was order hidden in disguise, a glimpse into the underlying code of creation. Decades later, as quantum mechanics matured, its consequences became clear. The technologies born from Planck's discovery reshaped civilization itself. Without the quantization of energy, there would be no semiconductors, no lasers, no computers, no modern communication networks. Every time a phone camera captures light, every time data flows through fiber optics, every time a computer switches a transistor, Planck's constant silently guides the process. His idea, once dismissed as a mathematical trick, had become the foundation of a technological revolution. Yet, beyond the machinery of progress, Planck's insight carried a deeper message. It showed that even the smallest things matter, that the universe itself operates on the rhythm of the minuscule. It revealed a cosmos where continuity is an illusion and precision gives way to patterns of probability. This was not merely a shift in equations, it was a transformation in thought. As the years passed, Max Planck's name became immortal. The unit of action, Planck's constant, became a symbol of the smallest possible quantum of energy exchange. The Planck length, the Planck time, and the Planck scale define the limits beyond which the known laws of physics collapse. His constant, once scribbled in quiet ink on a sheet of paper, now defines the boundary of the universe's smallest possible realm. In many ways, Planck's idea was not just about physics, it was about the nature of truth. It taught humanity that truth is not always obvious, that progress often begins in doubt, and that the universe may be far stranger and more wondrous than we can imagine. His discovery bridged the visible and the invisible, the known and the unknown. It connected the warmth of a glowing ember to the invisible dance of particles deep within it. From the dim laboratories of the 19th century to the quantum computers of the 21st, the thread of Planck's idea runs unbroken. It is the quiet heartbeat of modern science, the rhythm behind the light of stars, and the pulse of atoms. What began as a mathematical solution to a problem of radiation became the seed of a revolution that continues to unfold. And in the quiet moments of reflection, when scientists look up at the night sky or down into the smallest particles of matter, they still hear the echo of that idea. A whisper from Max Planck reminding us that the universe, in all its vastness and mystery, was forever changed by one thought. A thought that energy, like music, comes in notes, not in a continuous sound, but in the finite, distinct vibrations of creation itself. It was the moment when the infinite became countable, when certainty gave way to curiosity, and when science crossed the threshold into a new age. Max Planck's revolutionary idea did not just create modern physics, it illuminated the unseen architecture of reality itself. His quanta became the language through which the universe speaks, a timeless reminder that even the smallest spark can ignite the dawn of understanding. At the dawn of the 20th century, classical physics stood like an unshakable monument. For centuries, Newton's laws had ruled motion and force with precision. Maxwell's equations described light and electromagnetism in elegant harmony. Thermodynamics had codified the flow of heat and energy. Humanity believed it had uncovered the grand blueprint of the universe. Yet, hidden within the glow of heated objects and the flicker of light, nature held a secret that classical physics could not explain. That secret was the quantum, and Max Planck was the first to glimpse it. Planck's revolutionary insight, that energy could exist only in discrete packets called quanta, was not merely a minor adjustment to the laws of physics. It represented a fundamental challenge to the very foundations of classical thought. Classical physics treated energy as continuous, flowing like water or air without interruption. Heat, light, and radiation were expected to vary smoothly with intensity and frequency. Experiments, however, told a different story. The Blackbody radiation problem had shown that at high frequencies, classical theories predicted infinite energy, a clear contradiction with observation. This so-called ultraviolet catastrophe exposed the limitations of the old order and demanded a new understanding. By proposing that energy is quantized, Planck introduced an idea that was deeply counterintuitive. It suggested that at the microscopic scale, the universe did not behave as a continuous machine, but as a system of discrete events. Matter and light did not follow smooth trajectories or flow endlessly, they jumped, leapt, and transitioned in fixed increments determined by Planck's constant. The world, once imagined as a seamless continuum, was now revealed to be granular, its energy levels like the steps of a ladder rather than a ramp. The implications of this idea were profound and far-reaching. Classical physics relied on predictability and determinism. If one knew the initial conditions of a system, one could calculate its future with precision. The quantization of energy, however, introduced a new layer of complexity. At atomic and subatomic scales, events occurred in discrete bursts, not continuous flows. This meant that determinism was limited, and that probabilities became central to understanding natural phenomena. Planck's discovery suggested that reality itself could operate according to rules radically different from those governing the macroscopic world. The impact of Planck's work extended beyond theoretical physics. It forced scientists to rethink the very concept of light. Previously understood as a continuous electromagnetic wave, light now exhibited particle-like properties. Einstein, building on Planck's idea, proposed that light consists of photons, discrete packets of energy, which could explain phenomena like the photoelectric effect, observations that classical theories could not account for. The quantum hypothesis revealed a dual nature of light, both wave and particle, continuous in some contexts but discrete in others. This duality challenged the entire framework of classical mechanics and opened the door to a new scientific paradigm. Planck's quantum concept also reshaped our understanding of matter. Atoms, once modeled as tiny solar systems with electrons orbiting smoothly around nuclei, were found to obey strict quantized energy levels. Electrons could exist only in specific states, and the emission or absorption of energy occurred in precise steps. These principles explained the distinct lines observed in atomic spectra and laid the foundation for Niels Bohr's revolutionary atomic model. In essence, the universe revealed itself as a carefully structured system governed by quantized rules rather than by continuous flows, a radical departure from classical expectations. The challenge for scientists of the era was as much philosophical as it was mathematical. Accepting quantization meant questioning centuries of established knowledge. Classical physics had been comfortable, elegant, and predictable. Quantum mechanics was strange, probabilistic, and counterintuitive. Yet, the evidence could not be ignored. Experiments matched the predictions of Planck's formula with remarkable precision. The ultraviolet catastrophe was resolved, atomic spectra were explained, and the photoelectric effect found its solution. The discrete nature of energy was no longer a theoretical curiosity, it was a fundamental feature of reality. Moreover, Planck's work demonstrated the limitations of classical ideas about continuity and determinism. Heat and radiation, once assumed to vary smoothly, were now understood as sequences of quantized events. Classical laws remained valid at large scales, but they failed to describe microscopic phenomena. In this way, Planck's quantum hypothesis reconciled old and new physics. The classical world emerged as an approximation of the quantum reality at larger scales, while at the atomic level, the rules were fundamentally different. The broader significance of this breakthrough cannot be overstated. It marked the beginning of modern physics, a new era in which the microscopic and macroscopic worlds were understood through different lenses. Planck's quanta introduced concepts that would define the 20th century: uncertainty, probability, wave-particle duality, and the fundamental limits of measurement. These ideas would give rise to technologies that transformed human life, from semiconductors and lasers to computers and telecommunications, demonstrating that abstract theory could have tangible, world-changing consequences. Planck himself approached his discovery with humility. He often described quantization as a formal assumption, a necessary mathematical step to fit experimental data. He did not initially grasp its full revolutionary potential. Yet, history would remember him as the father of quantum theory, the man who first dared to see beyond classical certainty. His work exemplifies the essence of scientific progress: curiosity, patience, and the courage to follow evidence wherever it leads, even when it challenges deeply held beliefs. In retrospect, the quantum idea represents one of humanity's greatest intellectual achievements. It transformed our view of the universe from a smooth, predictable machine into a dynamic, probabilistic, and profoundly intricate reality. The classical world remained intact in our everyday experience, but the quantum world revealed the hidden structure beneath it, a world governed by discrete steps and fundamental constants. Planck's insight bridged these two realms, showing that continuity and quantization coexist, and that understanding both is essential to grasping the full complexity of nature. Planck's contribution also reshaped scientific methodology. It highlighted the importance of empirical observation over philosophical preconceptions. Where intuition and classical reasoning failed, careful measurement and analysis provided the path forward. The Blackbody radiation problem, once a perplexing anomaly, became the catalyst for a revolution that transformed physics. Planck's quantization of energy was not just a solution to a single problem. It was the first step toward a new conceptual framework that continues to guide scientific inquiry to this day. Ultimately, the legacy of Planck's quantum hypothesis is both scientific and philosophical. It demonstrates that reality often defies expectation, that the universe is more intricate than our senses reveal, and that progress requires openness to ideas that initially seem impossible. From glowing metal filaments to the farthest reaches of cosmic radiation, Planck's insight into discrete energy packets reshaped our understanding of the cosmos. Every photon, every atomic transition, every quantum leap carries the imprint of his discovery, a silent reminder of the subtle yet profound ways in which nature operates. In this sense, Planck's quantum is more than a physical concept, it is a symbol of human curiosity and perseverance. It represents the moment when careful observation, rigorous analysis, and bold imagination converge to redefine what it means to understand the universe. By challenging classical assumptions, Planck opened the door to a new era, one in which the smallest elements of nature revealed the deepest truths about reality. In the vast universe of physics, there exists a number so small that it seems almost insignificant, yet its impact is immeasurable. This is Planck's constant, denoted by h, a value so tiny, 6.626 × 10^{-joule seconds, that it is almost beyond human perception. And yet, Within this microscopic figure lies the key to understanding the fundamental behavior of nature. Max Planck introduced this constant in 1900, almost reluctantly, as a mathematical device to solve the problem of blackbody radiation. He did not initially foresee the revolution it would ignite. Today, Planck's constant is recognized as one of the most important quantities in physics, a cornerstone of quantum mechanics, and a silent ruler of the microscopic world. Planck's constant acts as a bridge between the world we experience and the hidden quantum realm. Classical physics assumes that energy can vary continuously, flowing smoothly from one state to another. Planck's constant shattered that assumption by establishing the smallest possible increment of energy that can be exchanged. In effect, it set a universal scale for the grainness of reality. Energy is not infinitely divisible, it comes in quanta, each precisely defined by h multiplied by the frequency of the associated wave. This simple formula, et hanem, would become the guiding principle of modern physics, governing phenomena from the emission of light by atoms to the behavior of electrons in solids. The significance of Planck's constant extends far beyond theoretical mathematics. It defines the scale at which quantum effects dominate. While classical mechanics can accurately describe the motion of planets or the trajectory of a thrown ball, it fails to explain phenomena at atomic and subatomic levels. In these domains, Planck's constant is indispensable. It sets the scale for energy levels within atoms, dictates the frequency of photons emitted in transitions, and underpins the uncertainty principle that governs the limits of measurement. Every electron orbit, every photon released, every vibration of an atomic oscillator obeys this tiny number. Consider the photoelectric effect famously explained by Einstein in 1905. When light strikes a metal surface, electrons are ejected, but only if the light has sufficient energy. This energy is not continuous, it comes in discrete packets, each defined by h. The constant determines the energy of each photon and, consequently, whether it can free an electron from the metal. Without Planck's constant, the explanation of this effect would be impossible. It connects the abstract world of numbers with tangible experimental results, showing that the universe operates according to quantized rules. Planck's constant also defines the rhythm of atomic and molecular transitions. Atoms can absorb or emit energy only in discrete steps, with h setting the scale of these steps. When an electron jumps from a lower energy level to a higher one, the energy required is precisely a multiple of h times the frequency of the emitted or absorbed radiation. This principle explains the spectral lines observed in atomic emission and absorption, the colorful fingerprints of elements. It is Planck's constant that transforms these observations from mysterious patterns into a predictable and understandable framework. The influence of h extends into technology as well. Modern electronics, lasers, and quantum computers all rely on principles derived from Planck's constant. Semiconductors operate based on discrete energy levels in atoms, which are governed by h. Lasers produce coherent light by controlling photon emissions, again dictated by the constant. Quantum devices manipulate individual particles and their interactions, all of which depend on the precise value of h. In this way, a number so tiny that it could be overlooked has become the foundation of much of modern technology, connecting theoretical physics to practical innovation. Even the fundamental units of measurement have been redefined using Planck's constant. In 2019, the kilogram was redefined not by a physical object, but by a fixed value of h. This reflects a profound truth that nature's constants, rather than human artifacts, define reality. Planck's constant is no longer just a number in a textbook, it is a universal standard, anchoring the scales by which we measure energy, mass, and time. Its role extends from the smallest laboratory experiments to the largest cosmic observations, uniting the microscopic and macroscopic worlds. Beyond its technical significance, Planck's constant symbolizes a philosophical shift in human understanding. It represents the first recognition that the universe is not infinitely divisible, that reality has a fundamental granularity. Classical physics, with its continuous curves and smooth flows, gave way to a new vision, a universe where energy is exchanged in precise quanta, where light behaves as both wave and particle, and where certainty is replaced by probability. This tiny number challenged centuries of assumptions and reshaped the very way we think about nature. In laboratories around the world, scientists measure phenomena that depend directly on Planck's constant. They use it to calculate the energy of photons in spectroscopy, to predict the behavior of electrons in quantum dots, and to understand the interactions of atoms at ultra-low temperatures. The constant governs the spacing of energy levels in atoms, the tunneling of electrons across barriers, and the vibration of molecules. It provides the scale for all quantum interactions, serving as the thread that links the behavior of the smallest particles to observable effects in our everyday world. Planck's constant also underlies the Heisenberg uncertainty principle, one of the most famous and counterintuitive results of quantum mechanics. This principle states that certain pairs of properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. The limit of this uncertainty is determined by h. Without Planck's constant, the probabilistic nature of the quantum world would have no quantitative foundation. It establishes the fundamental limits of measurement and knowledge, revealing the boundaries between what can be observed and what remains inherently uncertain. Despite its abstract nature, Planck's constant is deeply woven into the fabric of reality. It appears in the vibrations of atomic nuclei, in the glow of distant stars, in the light that passes through a prism, and in the behavior of particles in high-energy accelerators. Every quantum leap, every photon emitted or absorbed, every atomic transition is governed by this seemingly insignificant number. It is both a tool and a law, a bridge between theory and experiment, the key to unlocking the mysteries of the microcosm. In reflecting on Planck's achievement, one recognizes the extraordinary vision required to conceive of such a constant. He was not seeking to revolutionize physics, he was trying to solve a practical problem. Yet, in addressing the anomalies of blackbody radiation, he uncovered a fundamental truth about the universe. The discovery of H was a moment of insight that transformed our understanding of energy, light, matter, and the cosmos. What began as a technical fix became the foundation of a new worldview, giving birth to quantum mechanics and shaping the technological and philosophical landscape of the modern era. Planck's constant remains a symbol of scientific ingenuity and intellectual courage. It reminds us that even the smallest numbers can have enormous implications, that the tiniest insights can change the course of human knowledge. From the glow of a heated filament to the operations of quantum computers, from the spectral lines of distant stars to the precise calibration of our measurement standards, H governs the behavior of the universe at its most fundamental level. It is the heartbeat of the quantum world, a silent yet omnipresent measure of reality's structure. Ultimately, Planck's constant exemplifies the power of human curiosity. By daring to see beyond the apparent and questioning assumptions long held sacred, Max Planck opened a door to a universe of discrete energy, probabilistic behavior, and unimaginable complexity. This tiny number, once a solution to a practical problem, became a cornerstone of modern physics, guiding generations of scientists in their quest to understand the cosmos. Through H, the quantum world speaks to us, revealing the profound truth that the universe is made not of smooth flows, but of the smallest, indivisible packets of energy, each governed by a constant that changes everything. When Max Planck first introduced the idea of quantized energy in 1900, he could hardly have imagined the chain reaction it would ignite across the world of physics. His hypothesis, initially a modest attempt to solve the problem of blackbody radiation, soon became the spark that would illuminate some of the deepest mysteries of the universe. The notion that energy is exchanged in discrete packets, quanta, challenged the classical worldview and set the stage for a revolution that would redefine the very essence of reality. The implications of Planck's work became vividly clear just a few years later when Albert Einstein extended the concept to light itself. In 1905, Einstein proposed that light is composed of individual quanta, later called photons. This bold step explained the photoelectric effect, a phenomenon that had baffled scientists for decades. When light strikes a metal surface, electrons are ejected not in a smooth, continuous manner, but in abrupt bursts. Classical physics could not account for this, yet Planck's constant provided the key. The energy of each photon was proportional to its frequency. Einstein's application of Planck's idea demonstrated that the quantum hypothesis was not limited to thermal radiation. It applied universally, revealing a new structure to nature itself. This revelation was revolutionary not only scientifically, but philosophically. For centuries, physics had been dominated by the concept of continuity. Waves, forces, and motions were assumed to be smooth and infinitely divisible. Determinism reigned supreme. If one knew the conditions at a particular moment, one could predict the future with certainty. The quantum idea shattered this illusion. Energy exchanges were no longer smooth flows but discrete jumps. Light behaved sometimes as a wave, sometimes as a particle. Matter exhibited probabilistic behavior at its most fundamental level. Planck had set the stage for a universe that operated according to new and unexpected rules. Einstein's insight bridged Planck's abstract mathematics with physical reality. While Planck had initially viewed quanta as a formalism to fit experimental data, Einstein recognized them as real, measurable entities. By proposing the photon, he extended the quantum principle beyond heat radiation and placed it at the center of a broader understanding of the physical world. Suddenly, phenomena that had seemed anomalous or inexplicable were illuminated by a single, elegant principle: energy is quantized. The photoelectric effect became the first major experimental validation of quantum theory and would later earn Einstein the Nobel Prize in Physics. The ripple effects of this idea transformed atomic theory. Classical models of the atom could not explain the discrete lines observed in atomic spectra. The Bohr model of the atom, developed in 1913, relied directly on Planck's quantization principle. Niels Bohr proposed that electrons occupy specific energy levels and can jump between these levels by absorbing or emitting quanta of energy. The stability of atoms, the emission of light in precise frequencies, and the structure of the periodic table all became understandable through the quantum lens. A single idea, Planck's quantized energy, had cascaded into a comprehensive framework that explained the structure of matter itself. Beyond atomic physics, the quantum principle began to reveal its universal reach. It influenced the emerging field of statistical mechanics, redefined thermodynamics at microscopic scales, and even touched on the nature of light, matter, and radiation in ways that challenged common intuition. Experiments across Europe and America confirmed predictions derived from Planck's constant. The energy levels of electrons, the behavior of photons, and the statistical distribution of particles all demonstrated the discrete nature of energy exchanges. One by one, classical assumptions were overturned, and a new, more nuanced understanding of reality emerged. The transition from Planck to Einstein illustrates a remarkable aspect of scientific progress: that an idea introduced to solve a narrow problem can evolve into a principle of universal significance. Planck's quantization arose from the specific challenge of blackbody radiation. Einstein, recognizing its broader implications, applied it to light itself, fundamentally altering our understanding of electromagnetism and matter. The quantum concept, once a mathematical convenience, became a profound statement about the nature of the universe, that at its most fundamental level, energy, light, and matter are discrete, not continuous. This revolution was not only theoretical but deeply practical. Technologies that now define modern life, lasers, semiconductors, solar cells, and quantum devices, are rooted in the principles first suggested by Planck and extended by Einstein. Every time a photon is absorbed by a solar panel or emitted by a laser, the energy is quantized according to Planck's constant. The abstract, almost ethereal equations of the early 20th century became the blueprint for real, world innovations that shape daily life. The human aspect of this story is equally compelling. Planck was cautious, almost hesitant, in presenting his discovery. He did not anticipate the full consequences of quantization and initially regarded it as a mathematical fix. Einstein, by contrast, embraced the radical implications, taking Planck's idea and demonstrating its universal application. Together, their contributions exemplify the synergy between careful observation, creative imagination, and bold intellectual risk-taking. Science advanced not merely because of data, but because these individuals dared to reinterpret reality in fundamentally new ways. Moreover, the Planck-Einstein transition highlights a deeper philosophical truth that nature often resists simplistic explanations. The universe, at its smallest scales, is not governed by smooth, continuous laws alone. It operates according to discrete principles that can seem strange, counterintuitive, or even paradoxical. Energy comes in quanta light and photons, and electrons in defined levels. By recognizing and embracing these principles, scientists were able to uncover the hidden order of the microscopic world, paving the way for a century of discovery and innovation. The journey from Planck to Einstein is a story of intellectual courage and insight. It underscores the importance of questioning assumptions and listening carefully to the messages hidden in nature's anomalies. A problem that seemed trivial, the incorrect prediction of blackbody radiation, led to a discovery that reshaped the foundations of physics. The tiny constant introduced by Planck became a universal measure of reality, and Einstein's photon hypothesis extended its reach, revealing the quantum architecture of the universe. Today, we see the enduring legacy of this transition in every corner of physics. Quantum theory governs the behavior of particles, atoms, and molecules. It informs chemistry, material science, electronics, and optics. It challenges our intuition, reminding us that the world at its most fundamental level does not operate according to the smooth, predictable laws of classical physics, but according to probabilities, discrete interactions, and the inexorable rhythm of quanta. In reflecting on this era, one realizes that the leap from Planck to Einstein represents more than a scientific achievement. It marks a profound shift in human understanding. It reveals the universe as a place where the smallest ideas can have the largest consequences, where a single insight can redefine centuries of knowledge. It reminds us that progress often begins with a quiet observation, a careful calculation, and the courage to see beyond conventional wisdom. Through Planck and Einstein, we learn that reality is richer, stranger, and more intricate than our senses can perceive. Their work opened a door to the quantum realm, showing that the universe operates according to rules both elegant and subtle, rules that govern the flow of energy, the behavior of light, and the structure of matter. A single idea, introduced to solve a practical problem, became the seed of a revolution that continues to shape science, technology, and our understanding of existence itself. Max Planck's discovery of quantized energy did more than solve a specific scientific problem. It transformed humanity's understanding of the universe. Before Planck, physics had been a grand, orderly structure of predictable laws. Newtonian mechanics described motion with precision, and Maxwell's equations explained the behavior of light and electromagnetism in elegant continuity. The world seemed a smooth, comprehensible machine, yet in 1900 Planck revealed a deeper reality, one in which energy exists not as a continuous flow but in discrete, indivisible packets called quanta. This revelation challenged centuries of assumptions and laid the foundation for modern physics, creating a legacy that continues to shape both science and our perception of reality. Planck's constant, h, became the bridge between the known and the unknown. Tiny and seemingly insignificant, it governs the smallest units of energy that can be exchanged in the universe. From the flicker of a glowing filament to the behavior of electrons in atoms, from the emission of photons to the structure of matter itself, Planck's constant dictates the rhythm of nature. By defining a fundamental limit to energy transfer, It not only resolved the blackbody radiation problem, but also established a universal scale that underpins all quantum phenomena. This constant became the measuring stick for a new world, one that was discrete, probabilistic, and profoundly interconnected. The influence of Planck's work extends far beyond the equations he wrote. Niels Bohr applied quantization to atomic models, explaining the discrete energy levels of electrons. Einstein extended it to light, introducing the concept of photons and explaining the photoelectric effect. Heisenberg and Schrödinger later developed the mathematical framework of quantum mechanics, using Planck's constant as a central element. Each step of this progression illustrates the extraordinary power of a single idea. One insight can ripple through generations, reshaping not only scientific theory, but also the way humans conceptualize the universe. Planck's legacy is also a testament to the subtlety of scientific discovery. He approached his problem with humility, careful observation, and rigorous analysis. Unlike some revolutionary thinkers, he did not intend to overturn classical physics. His quantization was initially a pragmatic solution to an experimental anomaly. Yet, in addressing this challenge, he uncovered a principle of universal significance. His work reminds us that sometimes the greatest revolutions in science arise not from bold declarations, but from meticulous attention to the evidence and the courage to follow it wherever it leads. The philosophical implications of Planck's discovery are profound. Quantization suggested that reality, at its most fundamental level, is not smooth, continuous, or deterministic. Instead, the universe operates in discrete steps, where events occur probabilistically, and certainty is limited. This challenged the classical worldview that had dominated centuries of human thought, and forced scientists and philosophers alike to reconsider the nature of reality. The quantum revolution, sparked by Planck, redefined the relationship between observation, measurement, and the fundamental behavior of matter and energy. Planck's idea also inspired technological innovation that reshaped modern civilization. The principles of quantum mechanics, rooted in the concept of energy quanta, underpin semiconductors, lasers, magnetic resonance imaging, and countless other devices that define contemporary life. Quantum theory guides the development of computers, telecommunications, and even emerging technologies like quantum cryptography. The practical consequences of Planck's tiny constant illustrate how abstract scientific insight can translate into transformative real-world applications, bridging the gap between theory and practice in ways that continue to evolve. Moreover, Planck's work illuminated the profound interconnectedness of nature. By showing that energy and matter behave according to discrete units, he revealed patterns that extend from the atomic scale to the cosmic. Photons emitted from distant stars follow the same quantum rules as electrons in a laboratory. Heat and light, the building blocks of daily experience, obey universal principles encoded in Planck's constant. His discovery demonstrated that the universe, while complex and probabilistic at small scales, is governed by coherent, elegant rules that connect all aspects of existence. The human dimension of Planck's legacy is equally compelling. He remained modest throughout his career, often reluctant to claim revolutionary status for his work. Yet the scientific community recognized the transformative impact of his insights. He became a guiding figure in the development of quantum theory, respected not only for his intellect, but also for his dedication to rigorous, evidence-based reasoning. Planck's story illustrates the power of persistence, intellectual honesty, and careful observation in advancing human knowledge, showing that scientific progress is as much about character as it is about discovery. Planck's influence also extends into the ongoing exploration of physics today. Concepts that he introduced continue to shape research in quantum mechanics, particle physics, cosmology, and quantum computing. The idea that energy is quantized informs experiments at the frontiers of knowledge, from the behavior of subatomic particles in accelerators to the study of black holes and the early universe. His work created a framework that allows humanity to probe the deepest layers of reality, pushing the boundaries of what is known and revealing the elegance of the cosmos at scales once unimaginable. Ultimately, Max Planck's legacy is one of insight, courage, and enduring impact. A single idea, the quantization of energy, reshaped the scientific landscape and transformed our understanding of the universe. It challenged centuries of established knowledge, gave rise to modern quantum theory, and provided the foundation for technologies that define our era. Planck's constant, small and subtle, is a testament to the power of observation and imagination, a reminder that even the tiniest insights can have monumental consequences. Planck's discovery also serves as a philosophical beacon, urging humanity to reconsider the nature of reality. The universe is not merely a predictable, continuous machine, it is intricate, probabilistic, and governed by discrete units of energy. By unveiling this hidden architecture, Planck transformed not only physics, but also the way humans perceive the cosmos and their place within it. The quantum world, with its strange dualities and probabilistic behavior, invites us to embrace uncertainty, to marvel at the elegance of nature, and to recognize the profound interconnectedness of all things. Through his work, Planck demonstrated that scientific discovery often begins with curiosity, patience, and careful attention to detail. His approach, meticulous, thoughtful, and grounded in evidence, allowed him to uncover a principle that would ripple through generations, influencing countless scientists and transforming entire fields of study. From theoretical equations to practical applications, from philosophical reflection to technological innovation, the legacy of Max Planck is woven into the fabric of the modern world. In the end, Max Planck's contribution reminds us that the smallest ideas can have the greatest impact. A single insight into the behavior of energy, captured in a simple constant, opened the door to an entirely new understanding of the universe. It is a story of discovery, perseverance, and intellectual courage. Planck's work continues to inspire scientists, philosophers, and thinkers alike, a testament to the enduring power of human curiosity and the extraordinary capacity of one idea to change the world.